Just introduction for the day, and then we're going to start our lectures. Today is kind of land-based lecture day, and last night my daughters were helping me pick out my clothes, and I realized they fit the land theme, and I was like, oh, this is an opportunity. I'm going to try to theme dress the rest of the week. So I missed the cloud socks and the cloud earrings that I have yesterday, so I'll try to work those in later this week. So the first thing I want to point out, again, just the code of conduct. Make sure, if you're helping each other, there was a lot of good helping during the lab sessions, helping peers. Just try to do it. It seemed like it was all constructive. Share the air in terms of, making sure we're getting a chance around the room to have questions. I'm looking at you this side of the room. I don't know if people have moved where they are, but I felt like the questions were like this side yesterday. And then today's the first day of the Meet a Scientist lunches. You can go to that website or the document that I sent you. I also posted them here. So if you see your name, you can see the people you're scheduled to meet with, the room you're going to meet in, and then the people who are going to meet with that person. We've tried to put you in separate rooms. I'm wondering if I accidentally cut someone off here. I will check this spreadsheet, but we put you in smaller rooms just so you can have a quiet conversation. Sometimes the cafeteria gets really loud. So, and there is a cafeteria east end. That's like, if you walk into the cafeteria, there'll be a walled off partition, go through that door, and then it should be a little quieter in there. All right, so today, like I said, the agenda is more land modeling lectures. We'll have a lecture in the afternoon about simpler models. A couple things I just want to point out. So the lab today, the exercises nominally are working on XML changes. If you didn't finish the basics yesterday, that's okay, and we want to still help you get through that lesson before you move on. We're trying to have it be a work at your own pace, but we aren't really sure how, since this is kind of the first year we're doing it exactly like that, we're not sure how that will divide up. So don't worry if you didn't get yesterday's done, and we'll make sure that you get help on that today, and then you can move into the XML changes because you do need that foundation from yesterday to really be successful the rest of the week. If you got past XML changes, that's fine too. You can also move on to the next exercises. As I mentioned, at lunch, there's Meet a Scientist. And then at 1 to 1:15, we're going to have a group photo at the front door. So at 1, we'll try to meet in this front lobby area. I think we'll decide if it's too hot or if it's too bright to have it outside. We might just have it in the front lobby. But please come there and be in the picture again. And again, the shuttle will depart at 5. It left a couple minutes early yesterday, and I think a few people were like, oh no, and running, and there was a little chaos. We will make sure that it waits until 5 today. So I'm sorry if that was you. We will do our best. And then the last thing I wanted to bring up, I talked to you yesterday about we have an issue with we had a lot of issues yesterday with the reservations. So last night, we went in and we made some changes, so I want to just show you this so that it's hopefully more direct. So I think Cecile and others pointed you to under resources. There's a page, I slightly renamed it. So it's called NCAR HPC environment. All this stuff in yellow is the most relevant. So it has the project account for this year, and then it has the special queues. And what's really important is today we have 2 special queues, and they have different numbers for morning and afternoon. And so you're gonna need to set this in the morning and in the afternoon. So we've added the XML change command right here. You shouldn't have to set the project name every time. You should be able to just set the job queue. You will have to use the -- force because the CESM code has these scripts that check if it's a normal queue, so otherwise it would look for, premium or regular or economy, and it's like, this doesn't fit that, and that's why it's telling you, oh, I can't do it. So you need to set that force flag so that it actually does force it to be in the reservation. So you should be able to do that. I just want to show you briefly, the idea that we had this .profile file, if you source that every time before each lab, we've been updating it with the reservation codes, but I'm just going to show you what that is. So SSH, I'm just going to log into mine. It's hard to type when people are watching you. All right, we're waiting on the duo. Sometimes it doesn't work even for me, and it's slow. All right, so once you get that token response, it's like a pause, and it logs in. I have my own .profile, so I don't want to just copy the profile over because it'll overwrite all my own aliases and stuff like that, and I don't want that. So there are instructions at the bottom of this page. It's still logging in, that's why we're waiting. And it says, right here. If you already had an account on Cheyenne and you had a dot profile, here's what you should do for this session. If you have a brand new account, this is what those profile files are. So I'm just gonna go, let's put this path right here. So I'm just trying to show you this file. So we're gonna go to Glade P, CESM, tutorial, and then we wanna look at the profile. And if you look, this is the same for the TCSHRC file. It just points you to a different profile that's like, we just have a soft link in there. So what we really wanna look at is this tutorial profile 2023. So tutorial profile 2023, and you can see in here that we've already set the project name, so that should be set for all of you. And then we had a tutorial queue and the reservation in there. So if you sourced every time, it should set this before each of the sessions. But if you built the model in the morning and then you want to run it in the afternoon and the queues changed, you might run into issues. So this is why we're suggesting you just use XML change. I might actually just remove this tutorial queue thing from this file today. But when you log in for the first time, it'll automatically source your profile. But this is why we asked you to do it. And then we also have it load all the modules that you'll need for the tutorial. So Git and NCL and CView, all that stuff. So that's why we have this .profile file. I think a lot of people either didn't see this or it was a little bit confusing how it was set up yesterday, but I just wanted to point this out that it should be a lot clearer today. And we have the instructions specifically written here for how to change the job queue so that and you have to do that before you run the job. So there are ways to change it later that we learned about yesterday. But try to make sure you look at this today. And again, it's under resources and NCAR HPC environment. All right, we have one question and then we're gonna. Oh.
I think the script that is for C shell. So if you are on a bash shell.
Well, the .profile works with the bash. So we have instructions here. Check your shell environment. If you have a brand new account, it automatically defaults to bash. If you have bash, so you find out what it is. You either have bash or C shell. If you have bash, follow these instructions. And if you have T shell, follow these instructions. It's basically the same file, it's just the name of it.
So the last 2 lines of the code, that was for, I think, C shell. Have to make changes for the bash.
Okay, well, we'll double check the profile files today. Are there any other quick questions about that? I just wanted to make clear how to do this today since I think that was the biggest issue yesterday. And thank you to the people who sent me typos. I tried to fix those, and if you see more today, which will invariably happen, you can go ahead and continue sending them to me. You can just send them directly to me because Elizabeth just forwards them to me, so. All right, okay. Without further ado, let me log out of this. We don't need that. All right, our first speaker today is Dave Lawrence. He is, why can't it be found? Okay, hold on. I'm gonna re-download it. I don't know what happened. Okay, we'll just hang on. I'm gonna trade this first. Oh, I think that's incorrect. 9:15
Okay.
is
Right.
when the break will start. So there's I have to remember to use the microphone myself. So Dave will give a 30-minute talk, and then there's 15-minute Q&A after. At the break, there will be coffee still out there. The second morning break, we're trying to have the refreshments in the middle of the room so that we can have lines on both sides. I know yesterday there was a very long queue for that. And just as you're going through, remember that there are many of us, so take a reasonable amount the first time, and then if the line kind of dies down, you can come back and get more. I think that's true for all of them. All right, so without further ado, Dave is going to talk to us about the community land model. Dave is one of the interim directors for CGD right now, and he was the land model working group co-chair for many years and has been pretty instrumental in the community land model development. I feel like I first interacted with him about permafrost related things. I don't know if you have any time for that anymore these days, but yeah.
Great, thank you. Yeah, it's fun to be here. And yeah, actually I've been here at NCAR for almost 20 years, and I was one of the founders of the CESM tutorial, and it's really fun to see how it's evolved and grown over the years. It's much better than when I did it. Not surprising. So, okay, so I'm going to talk about the community land model, and how we represent terrestrial processes in the Earth system, and I'm going to try to demonstrate to you or convince you about the relative importance of land processes in understanding climate change, climate variability, and Earth system dynamics. So land modeling, I often start with this slide. This is a photo of my wife, who's an oceanographer, and this is our kitchen, and we have conversations obviously about science all the time, and so she's here, why are you here in the world and doing what you do? And so that's fun. And so, the answer, of course, from my perspective is yes, of course, land is really, why land mining is it important? Yes, it's very important. And there's many reasons, but one of them, I think the most important one is this, land is a critical interface to which humanity, all of us, and ecosystems also affects and is affected by, adapts to, and mitigates global environmental change. We live on the land, we're experiencing the way the land is sort of processing carbon, water, carbon, energy, momentum is affecting how we are, experiencing the world. But going into some more details, things that we care about, we're interested in land modeling is, first of all, land-atmosphere interactions. A lot of the first research into land stuff is on land-atmosphere interactions. And, the big question is like, say you have a rain event and it's really wet and you're getting a lot more evaporation and latent heat flux into the atmosphere, when and where does that actually lead to more rain? That's an important question, right? It's actually pretty complicated. I'm not going to get into the answers here, but it's a fundamental question that we're trying to understand. When does it lead to more rain? When does it lead to more clouds? So when, where, and by how much do land surface fluxes influence the atmosphere, surface temperature, clouds, precipitation, et cetera? And we found that there definitely are times when the land has an influence on the atmosphere, not surprisingly. And if you try to do, ask questions about predictability, like weather predictability or seasonal predictability, you find that if you condition your initialization of the model on soil moisture, you find that you get quite a bit of predictability, especially at the extreme. So really, really wet situations or really, really dry situations lead to a change in your predictability. And also it's interesting, we're seeing that as the world is getting warmer and a lot of the world is drying out, we're finding that there's stronger coupling between the land and the atmosphere, which is sort of probably changing how we're going to be able to predict weather in the future. And then land has a lot of influence on extremes. As I'm sure you've seen in the news, huge extreme events are happening all around the world. And if you look at these carefully, a lot of them you find out that they're more extreme because of preconditioning from the land surface. Like it was a dry year before a drought event, before an extreme event starts, it can actually be even worse. We care about land because of water. So land has strong feedbacks on drought and floods. That's not surprising, right? How much water is in the soil at the beginning of a drought or a flood event is going to have a big impact on how strong those droughts and floods are and how long they last. The snow has a big impact. There's the snow albedo and the snow soil temperature feedbacks, which are important forcers of the climate change system. So just like you'll hear about later in the week with sea ice declining, as that sea ice declines, it's reflecting less energy back to the space, so we're absorbing more. The same thing's happening with snow. As snow disappears in the long run due to climate change, which we can see here in this figure, that is having a feedback effect on climate as we're absorbing, as the land surface is absorbing more energy. It's important in terms of water and food security. More than a sixth of the world's population relies on water from seasonal snowpacks. We know that runoff is changing coming from these seasonal snowpacks. This is actually a pretty old study now, but it's even worse now that's showing that the snow is melting earlier and earlier, and that's leading to changes in how much water we can store on the land, provide for irrigation and things like that. And water-plant interactions is another one that you may have not thought about too much in your daily lives. And it's important for many reasons. Plants are using water, and how much water they use affects how much water is available just to go back into the rivers and that we can use later. An interesting sort of process that's happening under climate change is that plants are likely getting more efficient in their use of water as CO2 rises. Plants like the increased CO2, and they can actually use less water to take in the same amount of carbon dioxide. So that's actually a positive effect of CO2 in terms of water availability. And then people use land models to understand streamflow prediction as well. And then another topic is land use and land cover change. And a lot of the world has been affected by land cover change. I'm sure you've heard read many articles about deforestation in the Amazon, but basically throughout human history, we've been modifying the land surface. And at this point, about 25% of the Earth's surface land surface has been experienced land cover change. That's like a deforestation, removing trees. But in fact, it's even more of the area has experienced some sort of land management. Our human footprint on the land is so extensive. On the figure there on the upper right there is showing the human footprint on the land. And anything that's in a deep blue color there is where humans haven't really had much impact. So it's really just the desert regions and the high Arctic, pretty much, and maybe so the heart of the Amazon, but pretty much everywhere else, humans are having an imprint on the land. And so it's not just land cover change that matters, it's how we're using that land actually can have an effect on the surface fluxes, which then affect the atmosphere. And regionally, we can find that land use and land cover change, that's the acronym there, can be as impactful on surface climate as greenhouse gases. So there are places where if you look at the temperature results and you see that there's been a change in surface temperature, you can actually attribute as much of that to land cover change as it is to greenhouse gases. Now, that's not true everywhere, obviously, but in some places it's as important. And here's just an example of where irrigation, has mitigating heat extremes in parts of the world, especially in India, where the irrigation is really intensive. And then also, there's a lot of impact of land use change on carbon. So about a third, and this was now a little bit of an old slide now, but about a third of the total emissions that humans have sent up in the atmosphere effectively are actually coming from land use change, not from burning fossil fuels. Today, it's about 10% of emissions are related to deforestation, but over the whole history, it's been about a third. And that deforestation has many impacts. It has a surface climate impact, but it also has an impact on the ability of the land to take up carbon from the atmosphere, which we critically need. As we're releasing fossil fuels into the atmosphere and CO2 into the atmosphere, the land and the oceans are taking up a big fraction of that carbon. If you cut down those forests, the capacity to take up that carbon reduces, so it has an additional impact, so the loss of the additional sink capacity. And then there's a question about the effectiveness of afforestation and biofuels for CO2 mitigation, a really important research topic. To get to low climate change targets, we're going to need to take carbon in the atmosphere. We're going to need to use the land and probably the ocean, natural sinks, to be able to do that. And then there's also interesting questions about urban versus rural differences in climate change impacts, and especially we know that we're experiencing more heat stress in urban environments than we are out in rural environments, and that has a big impact on especially socioeconomically disadvantaged parts of the world. And then finally, in terms of carbon and ecology, carbon and nitrogen cycle interactions are really important, and their impact on the long-term trajectory of the terrestrial carbon sink is a really high priority research topic for land modeling. There's really a high uncertainty in this land carbon sink. As you're in this field, that you'll be familiar with diagrams that show a spaghetti plot showing that all the Earth system models around the world completely disagree on how much carbon will be taken up over the next century or so. And that's really important. It's actually, from the way I look at it, it's about probably the second most important uncertainty in the climate change problem, with clouds being the biggest one. The second one is the land carbon sink. And in this just example for the high emission scenario, it's leading to about 1.2 degrees C uncertainty on top of 3.7 degrees C warming. So it's about a quarter of the total uncertainty in terms of projections. There's questions about the vulnerability of ecosystems to climate change, as well as natural and human disturbances. We're interested in understanding how forests and grasslands and everything else around the world can provide ecosystem services. And there's also questions about ecosystem management to help mitigate against climate change. So these are all the questions we're trying to address with land models in the Earth system science, and there's others, of course. And to answer these questions, these models have had to become increasingly complex and comprehensive over the years. And I've been involved with our research team here and contributing to the development of these models. And so it started off, say, in the 70s and maybe late 60s, where the first land models were very, very simple, and all they were trying to do is provide some lower boundary condition for the atmosphere models. What are the surface energy fluxes? And then as they have evolved, we started to get more detailed, like understanding how plant canopies affect those fluxes, how plants and their stomatal resistance affects how much water is lost from models. Modeling soil moisture explicitly, modeling the heterogeneity on the land surface, all the very differences between forests and grasslands and urban areas. And then we've evolved to including lakes and rivers and wetlands and groundwater and dynamic vegetation, the carbon cycle, and then in the latest generation of models, accounting for land cover change, urban environments, nutrient interactions, crops and irrigation, and lateral flow of water. So, it started off as land as just simply a lower boundary condition for the atmosphere, to land as an integral component of the Earth system. So that's where we are now. And so this is what CLM5, the Community Land Model version 5, it's the version used in CSM2, looks like. So it's a very complicated diagram, obviously more than anyone can take in, but try to capture the complexity, level of complexity that we're dealing with within just the land component of the Earth system model. That's what's so amazing about these Earth system models, is the complexity that goes on in each different component is intense. And so each line on here is an equation or multiple equations. And so I think we've counted in the number of equations that make up the community land model. It's something like 600 equations or more that describe the community land model. So, but taking a step back and say all those detailed flux diagrams, it's hard to really track and look at it and understand in a single sitting. If you think about what is it really trying to do, fundamentally, a land model is representing the surface exchanges of momentum, energy, water vapor, CO2, dust, and other trace gases or materials between the land surface and the overlying atmosphere, and also provides runoff to the ocean, and potentially could provide also fluxes of like carbon and nutrients to the ocean, although our model does not do that currently. And then additionally, it's prognosing the land states, which is useful for a lot of reasons, including things like soil moisture, soil temperature, canopy temperature, soil water, snow water equivalent, carbon and nitrogen stocks in the vegetation in the soil. So that's fundamentally what the model is trying to do. And so, if you're kind of getting more in the depths of it, at each time step of the model, it's trying to solve the surface energy balance through a set of equations, which basically, calculate the net energy that's coming in from the atmosphere through solar radiation or long wave radiation, and calculate how much is reflected back to the atmosphere, how much is absorbed, and then from how much is absorbed, determining how much of that energy is then converted into latent heat flux or sensible heat flux, so the turbulent heat exchanges into the atmosphere, which of course then has an impact on atmospheric processes. And then also some of that energy goes into the ground. And then also at every time step, we're calculating the surface water balance. So, accounting for all these processes like canopy interception and throughfall, and how much is accumulated in snow, and how much gets into the soil, how much goes to surface runoff. All these factors are important parts of understanding the surface water balance. And then, ultimately we're trying to predict, how the soil moisture changes and how storage changes in the land, and how much, plants are using water through transpiration. And, the interesting thing, one of the interesting things about land modeling is that these, the energy cycle and the water cycle are like intimately linked. And so this is a nice quote from, a legend, one of the legends in the field. His name is Randy Koster. And, this is maybe not that surprising, but I think it's an important sort of synthesizing statement for land modeling, is that, the ability of a land surface scheme to model evaporation correctly depends crucially on its ability to model runoff correctly. The two fluxes are integrally linked through soil moisture. So you can't get one right without getting the other right. And you can see the complexity of why this is sort of hard, is that if you just sort of, it's a schematic diagram, if this is soil wetness on the x-axis here, and this is evaporation and runoff on the y-axis, you see that soil wetness has, for runoff, you get a little bit more runoff when soils are super, super dry. You can imagine that crusting of soil you see in the desert sometimes. And so there's a little bit of a peak in the runoff distribution there, but as you get a little bit wetter, comes to where the lowest amount of runoff, so the soils are absorbing a lot of water. And then as you get wetter and wetter, you're getting more and more. And essentially, at some point, it's totally asymptotic, right? You can't add any more water to the soil. We see that evaporation works slightly differently in that, there's no evaporation at really, really dry. There's no evaporation at really, really dry regimes. And then as you get a certain amount of wetness, it starts to evaporate, and it increases until, again, this one asymptotes in a different way. It can't evaporate anymore because there's not enough, energy coming from the sun. So these two fluxes, you can see how these curves are both nonlinear, and getting them both right is going to be a challenge, right? And then the surface carbon exchange, and you'll hear more about the carbon cycle in the next presentation, but trying to track how carbon is being taken up through gross primary productivity and then lost through heterotrophic and autotrophic respiration in terms that Adriana may explain better, and also losses due to fire and land use change. I'm not going to dwell on that one. Okay, so as I've sort of indicated a couple times already, it's a complex model, and I'm only going to be able to cover like a few things here in this presentation because there is so much going on in the land model, and you'll be able to look back through these slides and Adriana's slides afterwards to get more details, and then of course there's all the technical documentation online. But the model's made up a lot of parts: all the biogeophysical processes, photosynthesis, hydrology, snow, soil thermodynamics, surface albedo and radiative fluxes, and then a bunch of biogeochemistry processes related to how carbon and plants live and die, and the nitrogen cycle and methane production. And then there's sort of other submodels. There's an urban scheme, a scheme on crops and irrigation, a scheme that calculates how energy is being processed by lakes, glaciers and ice sheets, and there's a whole another ice sheet model that's separate from CLM. Fire and fire emissions, dust emissions, river flow, biogenic volatile organic compound emissions, just to name some of the key processes of the model. And this is just a slide I like to kind of put up here to illustrate, what we're talking about when I mean complexity. So on the other diagram, I had snow written as a couple boxes and a couple layers. Like it's not so hard. But it turns out these are all the things we're modeling when we're trying to model snow. We have these varying thicknesses that as the snow builds up, at some point you start off with one layer. That layer gets too thick to be able to numerically sort of capture the dynamics across the snow, so you adds another layer. The model automatically figures how to add another layer. More snow happens, it adds another layer. Snow melts, it loses a layer. So it's tracking that all the time. And then we're modeling accumulation and the fresh snow density, the snow melt and refreezing, snow aging, water and energy transfer across snow layers, snow compaction with various different processes that are leading to snow compaction, which affects the insulation, sublimation, aerosol and deposition, canopy snow storage, canopy snow radiation, snow barrier, snow cover fraction. So it's like a ton of things that we're doing in the land model, and so we'll still don't have it all right. We're missing key processes like blowing snow. We're missing subgrid variations in snow depth. We're missing depth Thor. And you're like, oh my God, do you really need to do depth Thor in an Earth system model? Everyone know what depth Thor is? I'm not actually going to answer that question. It's a layer of very light snow that forms when a certain temperature gradient, when it's really cold atmosphere. It's super important if you live in Colorado and you're a backcountry skier, because if there's depth Thor, it usually means there's like a high danger for avalanche. And I do a ton of backcountry skiing, and I'm always worried about the depth Thor. So you think, oh, do we need to represent avalanches in our model? No, we don't need to represent avalanches, but we do need to know that insulative layer that's happening. And it's really important in the permafrost domain, where that relatively shallow layer that's at the bottom of the snowpack is super light and causes super amount of insulation, and it's like super order one critical to understanding permafrost processes, and we don't represent it, and it's one of my favorite topics, so it makes me a bit upset. Okay, so I'm gonna run out of time, not be able to get anything, that's okay though. Okay, so fundamentally, what we're trying to do is understand, I kind of like to simplify it to this, is say we're trying to understand how plants and climate interact. So we obviously know that plants are gonna be responsive to climate, but we also know, you can anticipate that plants are going to be affecting climate as well. And so let's go through and think about how plants would affect climate. Okay, so this is the ways, the way they're going to affect the surface fluxes. So firstly, short wave. So plants are going to, affect the albedo, the amount of radiation that's reflected back to the atmosphere. And we know that the albedo varies by plant type. You can just see in this image, there's the dark trees, which are, conifer trees, which are dark. They're going to absorb more energy than those lighter trees, which are, some sort of like a birch tree or something like that. So that's going to have an impact on climate. Then there's also the long wave. So plants absorb CO2, so they're sort of pulling CO2 to the atmosphere. So that's actually reducing, the amount of energy that's being trapped by the atmosphere. But they're also releasing H2O, and water is a strong greenhouse gas. So these things are balancing each other out on daily, annual, and longer timescales. They also have an impact on the roughness of the surface, which affects the momentum transfer, and also affects how much energy is being put up in the atmosphere. So a taller tree compared to a shorter tree is going to have an impact on how much sensible heat flux is going to be sent up in the atmosphere, how much turbulent exchange is happening at the Earth's surface. So a rough surface is going to propagate more energy up into the atmosphere. And then, of course, they're controlling how much evaporation is happening from the soils by shading the soils, but also how much transpiration, which is how much the plants are using, and that's going to have a strong impact on the atmosphere as well in terms of controlling how much latent heat flux goes in the atmosphere. And they do this by how they control the transpiration flux of water through stomates and these little holes within the plants which are opening and closing to absorb CO2, and as they absorb CO2, they're losing water. It's actually what's happening, and so it's important to represent how these stomates are opening and closing, and we know that these stomates are opening and closing based on related to solar radiation, humidity deficits, soil moisture, CO2 concentrations, and the temperature of the leaf and the leaf nitrogen content. So it's a really complex process trying to understand how these plants are controlling the use of water. And so all these things taken together, you can see how a change in plants is going to exert a change in the surface energy budget, because each one of these processes is going to change. And so it's pretty complex. That's why you need to use an Earth system model to understand what the synthesized impact of a change in plants is going to be. And so, if you sort of kind of collectively try to say what our understanding is of different forests around the world, tropical forests we know are going to be strongly absorbing CO2 because they grow very effectively, and they're going to also lead to a lot of evaporative cooling. Temperate forests are going to have relatively strong CO2 absorption and relatively moderate evaporative cooling, and the boreal forests are going to take up relatively small amounts of CO2 because there's just not as much sunlight around to absorb, and they're going to have weak evaporative cooling. And if you try to think about which forests you want to preserve around the world, tropical forests are by far the most important forests for us to preserve in terms of climate change. They're in some ways they're a planetary savior. We should promote avoid deforestation and reforestation for sure. It becomes a little bit less clear in the mid latitudes about which is the most important. And then this is a bit of a joke, but the boreal forests are a menace to society. They kind of lead to warming, and so we should just get rid of them. We should not do that. But you wouldn't want to plant forests in the boreal region if you're trying to mitigate against climate change. Okay, and so the other complexity topic I like to raise is around land surface heterogeneity. It's one of our other key challenges. And you just look at these images to understand intuitively. We all live on land surface. We understand it's super complex. So how do we capture all this heterogeneity within an Earth system model? So in CLM, we have this concept called tiling, subgrid tiling. So if you have a grid cell, we can then split that grid cell up into different components. So with a vegetated part, a lake part, an urban part, a glacier part, and a cropland part. And then we also split it up further. In the vegetated part, you can have a soil column, and then underneath that, different types of plant functional types. So you can have the evergreen trees, the deciduous trees, grasslands, and maybe some sort of desert type of. So you can have as many different plant functional types on that tile as you want. And these are the list of the plant functional types that we currently represent. We got about 16 plant functional types. In the urban, I won't get into this, but there's all these complexities about how you model the urban environment in terms of its roof and shades and walls and impervious parts. In the glacier domain, we're accounting for the fact that, and especially in the glacier regions, we need to capture the gradients in the elevation that are really important, like on the edges of Greenland and Antarctica, and so we represent it by elevation classes. Then in cropland regions, we're trying to represent all the different crop types that we're growing around the world in both unirrigated and irrigated to try to capture all the impacts. So what you do is we look at MODIS information, so it's satellite information about the land surface, and combine it with lots of different data sources, and we can come up with, for each grid cell around the world, a weighted area for each one of these different land cover types. So this might be of 15% lake, 10% glacier, 5% urban, 50% naturally vegetated, and 30% crop in this particular grid cell. And so we do that for every grid cell around the world, and then we also use land use change maps to understand how that changes in time. I think I'm going to get into that in a second here. And so then I don't really have time to go through this, but we also represent land management in the model. So we have the crop model, we have irrigation, and we have fertilization. We're also accounting for wood harvest, which is a really important term in the carbon budget, urban environments, and anthropogenic fire ignition and suppression. And so if you're trying to understand landscape scale dynamics, how does land cover change affect things over time? You need to be able to change these weights. So each one of these arrows on here indicates what we call an allowed transition. And actually now we've made all these transitions allowed. We actually added the urban one last year. So you can change the area of any one of these on any time scale. We do it on an annual time scale. And so we have input data sets that we get from a different project called the Land Use Harmonization Project, which will then tell us that, from one time step to 1 year to the next year, you see here an example where we've like reduced the natural vegetation and increased the crop area. And so we do that within the model. We account for all the energy conservation we need. And here we can then capture the impacts of land cover change. Okay, I'm going to skip through this hydrology stuff in the interest of time. Another interesting example, and then get to the end and talk about CLM as a community modeling tool. CLM is awfully, and the land model working group, which sort of organized the development of CLM, we're coupled to community air system model, or it's actually coupled to other atmosphere models as well. And you use them all to understand what I've talked about here: land atmosphere interactions, climate variability, air quality, atmospheric chemistry, climate change, and weather. But of course, the interesting thing about CSM in general and the land community in specifically is that we're also working with these people who work on Earth system processes like an Earth system model. We also have a lot of people who are just interested in their own sort of little part of the scientific world. And so we work with people who are interested in societal impacts, hydrology, ecology, biogeochemistry, the cryosphere, agriculture, and forestry. And a lot of people just use CLM on its own as a research tool, either running globally or regionally or single point. And we have a really active development community across CSM. There's a lot of developers, and we're hoping that some of the people here in this room will turn into developers of the future. We really try to pull people in, and that's a lot. For CLM5, we had more than 50 people involved from 15 different institutions around the country and the world that were involved in the development of CLM5. And we focus on a bunch of things like how geology was more consistent with state-of-the-art understanding, more ecologically relevant, plant, nutrient, carbon, and water dynamics, more land management, prognostic greenland ice sheet model, and of course we're working on the next generation model now with a whole bunch of new things as well. I just want to kind of finish this talk with the last 2 minutes or so by indicating, you're going to learn a little bit about CSM during this tutorial this week, but nothing like the full scope of the ways the model can be used. It's like such a powerful tool. It's really an exciting tool. And here's just some examples, right? Just in the land component, we have built it so that it's very flexible. You can turn on and off different complexity layers. It helps you, ask different scientific questions depending on what's important to you. If you don't care about the carbons, like you might want to run a configuration of the model where you're prescribing the vegetation, so you can get the vegetation exactly right, or as close to right as we can, and then really interested in the atmospheric feedbacks. And other situations like in our BGC mode, we're actually trying to understand how the vegetation and climate interactions are working. And we also have examples like a configuration called BGC no anthro. So if you're interested in like paleoclimate configurations, you want to remove all representation of humans in the model, it's really easy to do. You turn on this flag that says turn off humans in the model essentially. And then another model, which I think Adriana will talk about, which is our advanced ecosystem model called FATES. We also can run many different spatial configurations, from global at both low and high resolution, regional, single points. We use tower sites a lot to force our model and understand, how the model is performing and how, how the world works at a local level. We can run on irregular grids like Q-sphere or even a catchment grid. And then there's different modes of forcing. So if you just want to run the land model and understand land responses to climate change, and you don't want the fully coupled Earth system model, which is extremely expensive, you can force the land model with what we call anomaly forcing, with a climate change coming from a previous Earth system model run from CSM or any other model, and we have it available working out of the box. We can force the model with many different observational data sets. We can prescribe, if we want to ask questions about soil moisture and how that's interacting with climate, sometimes it's useful to prescribe soil moisture, not let it vary, and then see how it compares to a run where the soil moisture is varying. We can do that. We can run different land use and land cover change scenarios, and we can couple the different models, including WRF. And then there's, you can turn on and turn off complexity. So that's another thing, turning on, turning on methane emissions or turning off methane emissions if you want to, turning on carbon isotopes and vice versa. And there's also other options that we have, which I don't have time to get in here, where you can increase complexity. So again, I'm just trying to illustrate the fact that this is a really powerful tool that, it takes quite a long time to understand the full scope of the tool, but once you do, you can understand that the number of scientific problems you can address with CLM and CSM is amazing. So this is, you'll have this there for resources. That's the slide I want to skip. And so then just to finish, we're working on many new things. Our priorities are really trying to understand these big topics. What is water and food security in the context of climate variability, change, and extreme weather? What is the vulnerability of ecosystems and the impacts on the carbon cycle to climate change? what are the sources of predictability from land processes, and what are the impacts of land use and land coverage on the climate, carbon, water. And we're doing a bunch of things to try to address this by adding reservoirs, for example. We're adding what we call a representative hillslope model to represent a lateral flow of water across the land surface. We're adding new irrigation methods, and we're adding multi-layer canopy to capture the dynamics of the canopy, and also a more advanced ecology model. So I'll stop there and take any questions.
All right, let's thank Dave. All right, like yesterday, I'm gonna run around the room and deliver microphones.
Thanks, Steve. Thanks for your introduction. So, as you mentioned, there are large uncertainties of the land carbon sink. So I'm wondering what is the largest uncertainties of the modeled land carbon sink? Is it because of the simulated respiration, or is it because of CO2 fertilizations, or some underrepresented processes such as nitrogen limitations? Thanks.
Yeah, I'm not sure I know the answer to that question for sure. I think my sense is that most likely it's the uncertainty in the CO2 fertilization. Is probably the biggest one. But it's probably going to depend on where you are around the world, is where the uncertainty is strongest. And Adriana maybe can comment on this more in her presentation. But one of the things that I didn't have time to talk about here, but I think is quite exciting, is that we're doing a huge parameter exploration of the model now. For the first time, we've been able to do it it's a whole presentation I could give on it. We have the ability now to explore the parameter space of there's more than 200 parameters in the model. And we have the ability now for the first time to explore that entire parameter space. And so we can actually it's allowing us to sort of ask this question, like, is it the parameters that are controlling CO2 fertilization, or is it parameters that are controlling nutrients, or is it parameters? And that will give us a pretty good indication of which part of the model is the most important. So we're pretty excited about this new capability, and hopefully eventually be able to, not even eventually, pretty soon be able to constrain the model with observations and hopefully provide some constrained projections.
Right. Could you say a little bit more about I presume it was methane from wetlands, or who I should speak to about that?
Yeah. So we do have a methane emissions model that's embedded within CESM. It's a process-oriented model. It's relatively complex. We haven't really spent a lot of time working on it in the last several years, and so my confidence in it is a little bit low, if I'm being frank about it. And I kind of say that also because the paper that we wrote about it back in 2012, when we first implemented it, I think the thing it said the title was like barriers to modeling methane emissions in an Earth system model, like even though we had done it. So so it's there, and it will give you methane emissions, and it's a good research tool. I personally wouldn't use it like out of the box and say this is a great representation of methane. I'd want to take a deeper look at it. So we do it. I will say also we do calculate how much surface water there is on the land, which then controls where the methane emissions are coming from, and that's a pretty complex and kind of innovative model that we have to sort of capture the amount of wetness on the surface, or where the water table is intersecting with the surface. So that's kind of a cool thing that we have in the model that is, again, it's ripe for use for sure, but I would not use it without a lot of care.
Okay, thanks Dave for the nice talk and for your efforts for 20 years developing the model. And I have a question for the dynamic vegetation, the phase model. For the phase, no matter the CRM phase or the ERM phase, I just see some papers about like only one side, just a single point. Is there not too much about the global scale things? So I want to know, we are using phase model to replace the DGVM model. So what's the develop of, I think the process of the phase model, where it is. Yeah. So whether this model is reliable now.
Yeah. So Adriana, who's going to speak next, is our local fates expert. So she can answer that. You can ask the question again to her. I'll give the very simple answer. It is mostly being used for single points or regionally right now, because it is quite hard to get it to work well, especially when you're turning on all the bells and whistles with all the competition that goes on. Adriana and others are actually involved in trying to calibrate the global version, and we are trying to get to the capability to run a global fates as a parallel to CLM. It would be CLM fates or ELM fates. We're working with the ELM team as well. So But we don't, I'm really hesitant to put a timeline on it because we're finding it to be quite a challenging process because it is such a process-rich model. It really has a lot of ways it can go wrong and also go right, of course. So it's definitely a high priority for us, but I can't tell you when we'll be able to run. We can run it globally now. We are doing it, but when it's going to be useful for like the big, large-scale carbon cycle assignments, for example, that we've been doing with CLM, I'm not sure. Adriana can add some more.
Hi, I had a question about the changing subgrid tiles. Are those driven by purely physical processes, or do they also interact and kind of feedback with human interactions, maybe depending on the SSP,
Yeah.
like changing urban and crop areas?
Yeah. Yeah, so the way it works is that we get so historically we've been able to through observations or inferred observations we can know where the what the land use was, right, and especially over the satellite record, and we can reconstruct a lot of it. So we're basically taking that information coming from all that and synthesizing it into this sort of annual maps of the land use every year. And then for the projection periods from the SSPs, the integrated assessment models that produce those provide land cover maps and all the different types. And so then there is a process that goes that sort of harmonizes these two things together. And so it is coming directly from these SSPs. And so anytime someone runs a new scenario, and in fact, I was just at a meeting about the next generation scenarios, a big thing we're thinking about is how are you going to produce the land cover maps that we'll then use to force the model. So yeah. And you could create your own, right? That's the other kind of fun thing is that we have done that, like a max reforestation. Like we try to look everywhere around the world where we could possibly plant trees, predictably without like removing all the food sources for the planet and try that scenario, right? And so those are the kind of experiments you can do with an Earth system model.
Thank you so much for your talk. I was wondering if it's possible for a user outside of NCAR to create more or new or custom plant functional types beyond the 16, and I'm asking from a paleoclimate perspective.
Right, yeah. So creating your own, there's two answers to that. One is that to add a plant functional type, unfortunately, a brand new one, like we have an array of 16 now, and if you added the 17th, is actually hard because of the way the code is written. But what people have done in the past is, especially if they're interested in a regional topic, or if there's some plant functional type that they don't feel like they need anymore, you can sort of take over that plant functional type in the code. And that's what people have done when they want to create a new plant functional type. And then it just comes down, I put in quotes, just comes down, to coming up with the parameter values for the 35 plus parameters that define a plant, to define what the plant is. And so that's what you need to do. So it is possible to do, and people have done that in the past. I will say one other nice thing about this parameter perturbation experiment that we're doing that if you're interested, I'm happy to talk to people more about it individually, is that we haven't done this yet, but we are intending to run the whole parameter perturbation experiment under like paleoclimates. It could be any paleoclimate, like the last glacial maximum was the one we're probably going to do first. And then just asking, like, because what we're pretty sure is that if we just took our parameter values that we have now, put them into the last glacial maximum conditions, a lot of the plants wouldn't survive those conditions. They're not adapted to it. So you could then recalibrate the model to build plants that would actually survive in the last glacial maximum. So we're trying to get to the point where it would be easy, relatively easy for a user to do that. I think within about a year or two, we should be there.
So you have given a very detailed account of the land model activity. So I have a question on two aspects. So you spoke on the snow modeling activities going on. So particularly over the third pole region, that is the Himalayas. So we are seeing that rapid snow melt has been taking place not only due to increase in temperature or aerosol deposition, but also due to increase in precipitation. So does the snow modeling aspect take into account the impact of precipitation because of which there is snow melt? That is my first question. And second thing, in the last decade, some work has been going on regarding the impact of soil moisture heterogeneity on extreme events development.
Mm-hmm.
So we know that there is in observations we see there is a lot of heterogeneity in spatial scales, but land models are not able to capture such heterogeneity.
Yeah.
So is there some work going on, and does the current generation or the future upcoming generation of the model, is it able to capture such heterogeneity and Is your group doing any work in this, like trying to assess the impact of the heterogeneity on extreme events?
Yeah.
These are my two questions.
Yeah. So the first question is, I think you're asking about, obviously we are representing Himalayan snow because it's an important part of the world. And I think you meant rain on snow events, right? Yeah. And so, yeah, it is captured by the model. Again, that's the kind of thing that we haven't looked at in a ton of detail. So I would want to go in and do, check to see whether or not it's capturing the change in snowmelt rate correctly if you're getting rain on snow events. In terms of heterogeneity, yes, we are trying to account for heterogeneity. There is actually a pretty big project that we're involved in right now called the Coupled Land Atmosphere Subgrid Processes Class Project. And we are trying to account for the impact of land surface heterogeneity on the overlying atmosphere, focusing actually more on how it's going to initiate convection and possibly clouds or rain, that heterogeneity, but you could easily extend that to ask questions about how that heterogeneity is affecting extremes. So yeah, we definitely have some interest in that. And likewise, trying to understand how, the heterogeneity that's induced by the atmosphere, essentially, if you think about a rain event, often it'll rain, here and then 10 kilometers away, which within the grid cell it didn't rain at all, right? And so capturing the fact that there's quite a bit of variation across the grid cell, that's the other thing we're trying to do. So yeah, it's something we're working on. Yeah.
All right, we're going to do 2 more questions and then go to break. And hopefully, if Dave's around, you could come if you have more questions. So 1 here and then 1 here, and we're done for this session.
Thank you for your presentation. My question is, how well does CESM model crop water use, including CO2 fertilization and irrigation, compared to other crop models currently available, specifically for future projections?
Yeah, I don't know. I wouldn't be able to answer in a comparative sense. CLM has participated in a few crop modeling and comparison projects, and actually Sam Rayburn I saw walked into the room. Where's Sam? Yeah, in the back. He's working here at NCAR and has been involved in crop modeling comparison projects, and is involved in trying to get CLM into some of these. And so I don't know the details of how it compares to other models. It is representing these processes, how crops are using water, and how much irrigation we need. And Sam and I were both just at an irrigation workshop a few weeks ago, and as far as I can tell, we're in the ballpark of all these models. There's a huge uncertainty across all the crop models too. So, and in fact, we had I'd say an hour-long discussion about how much irrigation is happening on the world, and nobody could agree. It was like at least a factor 2 to 3 times difference in how much water is being applied across the world, with all the experts in the room. So I can't really be a comparative answer, but we do represent these processes.
Thank you very much for your presentation. I was just wondering, what type of agricultural land use did you use in the model to capture different agricultural crops, fluxes, contribution to solar radiation dust reflection?
Yeah. Yeah, so the model has, our crop model has, represents processes like irrigation, fertilization. Something that we're working on now is on tillage, till or no-till practices. Those are the main management processes, and then we have 8 different crop types and 2 biofuel crop types to try to capture the global crop types. And then each one of those crops is going to have different planting seasons. Another project that Sam was working on is trying to make it so we can explicitly set planting dates to be so it's more realistic rather than having the model try to anticipate the planting date. So I think we have enough variability or enough representation in the model to capture some of the biggest impacts of crops on climate and how crops are going to respond to climate. But there's definitely a lot more things you could do. You can pest management. You can imagine about multi-cropping. You can having intercropping. There's a whole bunch of different processes that people are talking about in our community to make the model more and more useful for more detailed questions about agriculture. So.
All right, thank you so much, Dave. We're going to go to a break now. We'll see you back in here at 9:30. So sorry, we're a few minutes late. There's coffee, bathroom, stuff like that, and the food will be at the next break.
Thank you, everyone.
Okay. Let's get started again. Okay. So we're going to continue with our land modeling. All right, I'm going to wait for people to kind of finish their conversations. So we're going to continue with the land modeling. We're going to move more to biogeochemistry. Our next speaker is Adriana Foster. She's a forest ecologist in the terrestrial sciences system. As Dave mentioned, she works a lot with FATES, though she also works with CLM. And she's interested also in remote sensing of vegetation characteristics and the interactions between disturbance, vegetation, and climate. So without further ado, let's let Adriana go ahead and start.
Is this, did I do that? Is this on? We'll take a second maybe. Oh, okay, there we go. The green light came on. Okay, great. Thanks. Yeah, so Dave gave really great parts of what I'll was planning to cover, so I'll breeze through some of those. But yeah, part of my job, I think, is to get you excited about land biogeochemistry. And in CESM, this is mostly the carbon cycle, also sometimes the nitrogen cycle. Like living things are pretty much carbon, hydrogen, and oxygen in relative ratio of CH2O. So we're just kind of bags of carbon and water, and plants are just tubes of carbon and water. But anyway, so how many of you would consider yourself biogeochemists? Oh, we got like 2, 3, 4, 5. Okay. What about ecologists? Any ecologists? Oh, sweet. Okay, good. Awesome. All right. Yeah, so I consider myself a systems ecologist. I don't know. But anyway, so today I'm going to talk about land biogeochemistry in CESM, particularly why. Dave kind of already covered a lot of the why, but how, and then uncertainties and future directions. So let's talk about the why. Yeah, so how does, kind of a big question that is maybe recent, how does climate impact vegetation? But it's also this question springs from the deepest roots in ecology's history. So this is a schematic of a cross-section in the Andes Mountains that Alexander von Humboldt made. He did this trek in the early 1800s through the equatorial Andes. And he has all these plant species listed according to the altitude at which you can find them. And this was kind of like a big thing to think that, oh, plants are affected by climate, and they're affected, they grow in specific areas depending on the climate. So closer to home for NCAR, these are Miriam life zones looking at the zonation of vegetation within the San Francisco peaks. This is near Flagstaff, Arizona, as controlled by temperature and moisture. So as you go up a mountain, you get cooler temperatures, more moisture, and you get different species zonations. Globally, we can think about these things called Holdridge life zones. So this life zone system, it relates climate in terms of potential evapotranspiration, annual precipitation, and temperature using these indices. So basically we're looking at temperature and availability of moisture to plants. And so we can kind of categorize all of these, where vegetation can grow, what types of vegetation can grow based on climate. So I think we can all agree that, yeah, climate impacts vegetation. That's really important. Maybe what's going to happen when climate changes? We probably would think that vegetation is going to change. But then the opposite is also true. Vegetation impacts climate. So on short time scales, this is basically dominated by albedo and evapotranspiration signals. So this is a study by Liu et al. In 2006. They looked at photosynthesis impact on lagged temperature and precipitation globally. And so you can look at the shading corresponds to the strength of the feedback. And so we can see pretty strong feedback, positive feedback between temperature in the boreal and Arctic zone. I also disagree with Dave that the boreal we should cut it all down, because we have to remember that there's permafrost under there. And so if we cut all of the trees down, what's going to happen to the permafrost? There's a lot of carbon there. But anyway, okay, so and then there's some precipitation feedbacks as well. And then over longer time scales, it's really about the fate of carbon. So this is atmospheric CO2 at Mauna Loa. You've probably all seen this graph a billion times, but okay, what do you notice? What's like the big thing that you notice about this graph? It's increasing, right? So it's upward trend due to human activities. Wow, look at that, pretty grim. Okay, what else do we notice about this graph? Yeah, annual cycle. Yeah, there's this up and down due to vegetation. So yeah, here we can look at, this is MODIS NDVI. So basically we have this interannual variability in the land that we can see in the atmospheric signal. So this vegetation is crucially involved in the storage and uptake of CO2 in the atmosphere. So we can really see, basically the land breathing, and we can see this in the atmosphere. So we can look at where our emissions are going. So this is total emissions. In gray is the fossil emissions. In orange is land use change, so deforestation. Until about 1920, it was mostly, the emissions were mostly due to land use, land cover change. Now it's mostly fossil fuel. And so this graph is based on data. So this is based on energy statistics, cement production data, and then land use and land use change data. And so this is like 670 gigatons total emissions, nearly a third from land use, land cover change. Before 1920, it was mostly land use, land cover change. So where is it going? A lot of it's going into the atmosphere, as we saw based on the Mauna Loa curve. This is also based on atmosphere or observations. Some of it's going into the ocean. About a quarter of it is going into the ocean. And then this dotted line is sort of the opposite of the total emission. So where's the rest of it going? The land, yeah, right. So we have this land sink. This is based on global DGVM. So we have this land sink, but we also have a lot of interannual variability, mostly also due to land. And then we've got some budget imbalance, so we don't actually quite fill up all of the emissions. So this budget imbalance is driven by basically uncertainty in land, really. Okay, so we can look at the global carbon cycle, which is a lot of what this biogeochemistry in CESM is. So you notice there are these, okay, here's our emissions from fossil and forest fire farming. But we also have these huge pools. So land biota, 450 gigatons, soil, 1,700, permafrost, it's a lot, 1,400. And then we've got, oh, and also interestingly, the connection between the land and the ocean is actually pretty weak. There's not a lot of transfer, but it is there and it's important. And then the sink into the land is this residual. Oh, we've got these huge fluxes between photosynthesis and respiration, soil respiration. And that's about even, but then there's this residual that's the land sink. And so we notice there's substantial carbon fluxes into vegetation. Coupling between the land and ocean is a little weak. And then there's about 3 times as much carbon in the soils as in the biota. And so yeah, we get this land flux that we're really, this sort of annual flux is what we're really concerned with in CESM and CLM. It's this land breathing. And so kind of how do we do this? So this is the Bretherton diagram. You may have seen this. This Francis Bretherton was the director of NCAR in the late 1970s. He was a huge leader in Earth system modeling. Before this, land modeling was kind of seen as fairly tangential to climate modeling. Basically, land was just kind of like a boundary condition for the rest of the climate. And so adding terrestrial and marine biogeochemistry was one of Bretherton's big contributions to Earth system science. And so the focus here is on the interactions between the geosphere and the biosphere, with human forcings represented as like an outside force. Though, kind of one, well, I'll get to that later, yeah. And so then this launched into this what's called the Flying Leap proposal by Nets Fung, Peter Rayner, and Pierre Friedlingsting. It's like 23 years ago. This is an idea to have prognostic CO2 in the atmosphere from Earth system models. So rather than saying this is how much CO2 is in the atmosphere, we're actually going to try to simulate it. And this matured into a figure like this, showing that the link between CO2 emissions and temperature change is crucial. So then it depends on the emission scenario that you choose. And then that impacts how much warming you'll get. So crucially, we need to understand the carbon cycle in order to predict temperature change. So NCAR and CESM were these key players in the development and concept of the creation of the first coupled carbon cycle models. That culminated in this Flying Leap proposal, and then that all led into these C4 MIP type experiments. And then since then, well, I guess, okay, if you ask Dwight Schrute, he wants to know what's the most important element in the production of above ground leafy growth? Probably phosphorus, right? Yeah. No, it's nitrogen, okay? Yeah, right. So we added nitrogen. We're actually the first model in CESM, the first Earth sensitive model to include nitrogen in carbon cycle predictions in CMIP5. And then more recently, and in CMIP6, we were the first group to have explicit crop management in CESM too. So we're getting better and better at representing the complexity in the carbon cycle processes. So yeah, we can do these kind of idealized experiments of like injecting CO2 into the atmosphere. Let's do like 1% of CO2 increases per year. And then we can look at how the land and ocean uptake that, how much the ocean took up, how much the land took up. So these are idealized because we're forcing CO2. And then we're also kind of changing the way that the Earth responds. So we can do this fully coupled system where the land and the ocean and the atmosphere are all coupled together. They're interacting. Radiative forcing is going back to the atmosphere, feeding back on one another. But we can also just look at biogeochemical coupling. So that means that the land and ocean are affected by increased CO2, but then that CO2 does not affect temperature. And then we can also look at the opposite. We can have the land and oceans impacted by increasing temperatures from CO2 increases, but not the actual increase in CO2 itself. So the land doesn't really see that there's elevated CO2, it just sees that there's higher temperatures. And so these are this kind of cool hypothesis testing we can do with these types of models. Okay, so here's looking at the cumulative land CO2 sink in the fully coupled simulation. All these different lines are different CMIP6 models. There's no land cover change here. And this 1% increase is a somewhat realistic amount of CO2 increase over 140 years. Is 1% per year. Okay, so what do we see? What's like the big thing that we see here? Disagreement, yeah, there's huge uncertainty, definitely. Yeah, so we basically have no idea, what is the magnitude of the land sink? We don't know. Oh, there's CESM, and actually you can't really see it, it's behind the brown line, but CESM is there. Okay, so here's the biogeochemically coupled simulation. Still disagreement, okay, why, it's increasing, so why is the land sink increasing here? Or anyone? Probably CO2 fertilization. So the plants, they're seeing more CO2. They're happy about that. They can take up more CO2. They can do more photosynthesis. And then here's the radiatively coupled simulation. So the plants are not seeing increased CO2, but they are seeing increased temperature. Everyone's decreasing. We're actually a little bit more in agreement now. So I think I would agree with Dave when he said that the CO2 fertilization is a huge source of uncertainty, or at least it creates a lot of uncertainty when we add that in. Here's the ocean, cumulative ocean sink. Wow, we really got our ocean down. I think, you know, a lot of the ocean dynamics is, at this scale, is just physics, and so the physics is a lot more constrained. When we add in biology, like with the land, or even if we looked at a smaller scale at things like biogeochemistry in the ocean, we would definitely have a lot more uncertainty. And so that's kind of part of why the land is so cool, but it's also really hard, is because biology is just inherently complex and random, and it's really hard to model these systems. Okay, and then importantly, this spread in the land is affecting actual temperature. So this is global average surface temperature, and we see this huge spread in the fully coupled simulation that we believe is driven by this land spread. So the land is really important, and we really need to get it right. Okay, so going back to this Brotherton diagram, you might have seen this diagram yesterday, but this is all of the different component models in CESM. And then here's the land biogeochemistry, and then the land over on the left. I'm a little bit, have a qualm to pit, well, whatever. I don't know why there's like two boxes. I guess we inherently kind of are decoupling, especially, I mean, even in this Brotherton diagram, they separate biogeochemistry and then this like terrestrial energy and moisture exchange. We kind of separate them somehow conceptually in our minds, even though they're inherently linked. The physical and the biogeochemical processes are inherently linked in reality. And so I think, you know, we do have a coupled model in CLM5, but I think even just thinking about it in this conceptual way, I think it's problematic, and I think we should put them together at some point. Okay, so how do we do this? With a ton of contributors. So we have university collaborators from all over the world. There are over like 150 co-authors on the CLM5 documentation paper. So a lot of these people are here at NCAR, but then a lot of the other people are from our university collaborators and other national labs. And then maybe you could be here one day. So just think about if you would like to contribute. You can, after this, you can come talk to any of us. You can get involved by forking the code, doing model development, or just model application. Yeah, there's kind of a wealth of different questions that we're still trying to answer. Okay, so these are all the processes that we're trying to represent in the land surface model. Dave kind of went over them, but I'm going to zoom in on the carbon cycle. So here are the sort of the stocks, the fluxes we're trying to represent in carbon and nitrogen. We also have disturbances like fire, and then we want to look at both above ground, so like plant canopies, and below ground soils. This is a really great book by Gordon Bonin, who's here at NCAR, and lays out at a really high level what we are trying to do here. So this, if you're interested, you can get that book. You can maybe even get him to sign it. And then you can check out our code on GitHub. So we very much welcome contributions from external collaborators and developers. And so you can get the code. You can see we have, this might be old because it says we only have 520 issues. I think we have way more than that at this point. But yeah, there's issues you can try to fix. A lot of the issues are like features that we should be adding in the model. So yeah, have at it. Okay, so at a high level, what we're trying to do, as Dave said, is represent plants and their interaction with the environment. And that really, at a sort of fine scale, is leaves. And so we represent leaves through photosynthesis, through the Farquhar photosynthesis model, and then the Medlin stomatal conductance model. That used to be Ballberry stomatal conductance. Now we do Medlin. Medlin kind of allows us to do more PFT variations. And then we need to scale up to the canopy. So we do that, we scale up to the canopy, and then we have to calculate light transmittance, absorption, and reflectance through the canopy. So we do that right now through what's called the two-stream approximation. And we represent this essentially as one big sunlit, one big shaded leaf. It's a fairly simplified look at what actual forest canopies look like. I'll get back to this a bit later. And so then when we get out of this is GPP, or gross primary productivity. We then have to have the plants allocate that carbon to different tissues, and respire. So they respire, and then they allocate to leaves, wood, and roots. We have the coupling between GPP and respiration is pretty tight in CLM, so this actually leads to kind of dampened interannual variability, so that's something we're working on. But when we get this, we get autotrophic respiration, which then we can give us net primary production, so GPP minus AR. Then we also have to worry about phenology, so that means like mortality and turnover, so this breathing of the land on an annual scale, and that depends on whether it's evergreen or drought or stress deciduous. This is really tricky in a coupled model. If we don't really care about the biogeochemistry, we just want to say like, well, I know it's green in the summer, it's brown in the winter, like it actually kind of makes things easier, but when we do want to have all the bells and whistles all connected, it makes things kind of difficult. So this gives us the ELAI, so exposed leaf area index. Then we also need to look at leaf turnover mortality. That leads to decomposition. And so all of this happens in CLM. Yeah, and that gives us heterotrophic respiration. Okay, so here are all these fun acronyms. We get GPP, AR, NPP, ELAI, HR, and then at the end of it, we can get NEP, which is basically just GPP minus AR minus HR, and EE, which is NEP minus fire, so we have loss of carbon due to fire, and then NBP, which is minus land use and harvest. Okay, but these are really tricky because the leaf area affects GPP, so we have more leaves, we do more GPP, and then heterotrophic respiration also affects GPP through nitrogen availability. So when we connect all of these things together, we end up getting these nonlinear interactions and feedbacks, and that's kind of what makes the land difficult. Okay, so Dave showed this. What I was going to zoom in on is this patch scale. We've got different PFTs on their own soil column, or the PFTs are on one soil column, and then the crops are on a different column. Oh, yeah. And so, as I said before, plants respond differently to their environment depending on species. I mean, there are hundreds hundreds of thousands of species on Earth. So we can't represent them all individually, unfortunately. So we group them into what we call plant functional types. So right now in CLM, we have things like evergreen, deciduous, trees and shrubs, grasses, and then tropical versus boreal, and temperate. And so we have 16 PFTs right now. We also have these crop functional types, so we do represent crops in CLM. And so yeah, the natural vegetation is on its own column, and that shares a soil column. And then we have a separate column with crops, each with its own column. And that's for like rain-fed irrigation type purposes. And so yeah, we do agriculture in CLM. The most recent released version of CLM includes the option to use the crop model, and crops are simulated prognostically. So we simulate 11 crop types. We don't do tree crops right now, but that's kind of an area of active research. And then we also have that corn and soy has temperate and tropical varieties. And then we have winter wheat and 2 actually biofuel crops. And so then we do fertilize and irrigation. And so this management is really important for the carbon cycle. You can talk to Donica Lombardazzi for more on this, or Sam Rabin, who's actually in the back. Okay, so where do these parameterizations for plant functional types come from? So first of all, mostly it's fundamental understanding of plant physiological processes. So for example, the Farquhar photosynthesis, we're co-limited by light, energy, and the export of sugars. We also look at empirical relationships, so from a large sample of from the real world as possible, so this TRI database. So we can look at, for example, leaf nitrogen and dark respiration. And then we also think about optimality theory. So we kind of assume that plants try to optimize things like water use efficiency. And that's where this FUN model, which is, I don't know what that stands for. Plants, well, someone will maybe tell you, but plants look for the cheapest source of N, they pay nitrogen, they pay a carbon cost, and then the Luna model, which optimizes VC-max and J-max, which are photosynthesis parameters. And so some of these characteristics are data constrained and measurable, and some are not, and so it's really hard to do this. This is kind of leads to this large problem of calibrating the model. Dave kind of alluded, we're doing this big perturbed parameter ensemble experiment where we perturb all of the parameters in the model, and then after we figure out the sensitivity of these parameters, we then try to calibrate. But it's kind of hugely difficult. Yeah, so uncertainties and future directions. Okay, well, we're doing a pretty good job, actually. So the red line is the CESM1 cumulative land sink. The black is basically observations. And then the blue and green are CESM2. So we're actually representing the land sink now. Before it was negative. So this is good. We're actually representing the land as a sink now. We're objectively getting better and better at representing the carbon cycle as our model improves. So I don't know if you've heard of ILAM. It stands for the International Land Model Benchmarking Package. So it's basically a collection of data sets and then a Python package to evaluate land model outputs. So we can see, here's in green the carbon cycle. Basically, CESM2 is much better than CESM1 except for soil carbon, but I've heard that that's not our fault. It's the atmosphere's model fault for snowing too much. This is what I've been told. Don't come at me, though, if you're an atmosphere person. Okay, so we're doing better. This is great. And Dave showed this figure, but I just wanted to kind of highlight that, in the 70s, land kind of started out, at least in Earth system modeling, land started out as kind of a lower boundary of the atmosphere, and then we get more and more complex. Now we really recognize that land is an integral component of the Earth system. Yeah, and so some of our priorities in the land model working group, what we really want to know is how will ecosystem function and vulnerabilities transform under climate change? And this requires the synthesis of all we think that we know. So the physiology of plants and animals, population and community ecology, ecosystem productivity, and element cycling. And so there are some things that we're doing in the land model working group to try to improve our understanding and simulation of these processes. So one of the things that we're working on is the representative hill slope model. So this kind of breaks up CLM into these different hill slopes by aspect, and that allows us to get this really cool feedback of hydrology to biogeochemistry. You can talk to Sean Swenson if you're interested in that, but importantly, we kind of know that these aspects are really important. And we have a big tile that we're simulating on the land. We actually don't get these like fine scale topographic effects if we just say like, okay, well this 1 degree is like just one elevation, one aspect, one slope. We know that these topographic complexity really does impact biogeochemistry and land surface fluxes. And so we can do that with this module. And then, so if I'm going to bring you back to this figure, so remember how I said that plants have an impact on the climate and key through changes in surface roughness, evapotranspiration, albedo. Well, forest height, structure, age, and competition all affect these things. And so basically in the 70s, scientists recognized that forests are a mosaic of patches. So we can kind of see here's like a gap, here's a dying tree, and then here's some young trees. Okay, and then so forest dynamics are like the average responses of many such gaps. If we were going to look out across this landscape of forest, we see lots of different gaps. And essentially what we're seeing is this vegetation dynamics over time. So some of these gaps are in an establishment phase, some are growing, and then some are dying. And so if you look at one gap over time, you'll see this cycle of vegetation. And so that's what we're trying to represent in FATES, the Functionally Assembled Terrestrial Ecosystem Simulator. So we're trying to represent both these fast fluxes, you can see, like in big leaf, what we call big leaf CLM, so water and carbon fluxes, and a 30-minute time scale, but then also these vegetation dynamics. So here's just a little animation. So we can see when, say, like a fire happens, we get a gap, we do get these fluxes, and then we get growth over time. And so we get this daily growth and allocation in FATES of individual trees. And we're actually representing the trees as cohorts, so not strictly individuals, but we're grouping these individuals together based on their age and size and PFT. So yeah, we're getting dynamic vegetation. And there's a host of people who mainly work on FATES, but really we also have a lot of external collaborators. And so if we look at, on the left, this is kind of how we would represent plant functional tiling in CLM, the regular CLM. So each PFT kind of has its own tile. In FATES, we're actually working on a time since disturbance tiling. So each one of these patches or tiles has a specific age since it was last disturbed. And disturbance could be fire or tree fall or harvest and kind of whatever you want to put in the model. And then within each tile, we've got cohorts, so groups of plants defined by their PFT and size. And so with this, we think that we are getting much better at actually representing how forests interact with their environments, how they respond to the environment, and how that impacts the environment. And then we also are looking at this mimics, which is a module. So we've got lots of different PFTs in the plants. We also got PFTs in the ocean, plankton. What about the PFTs beneath our feet? So mimics kind of considers diversity in soil microbes. So that's pretty cool. Okay, so I'm just going to leave you with this sort of like big slide of like how are we going to understand how ecosystem function and vulnerabilities transform under climate change with hopefully CTSM and then all of these new developments we're going towards. And yeah, with that, take any questions. Thank you.
All right, thank you, Adriana. Okay, so we have some questions. Give me a second here.
Thank you for your talk. That was super informative. I have 3 questions, but answer whichever ones come to mind because I'm sure there's a lot. So one, what's the highest resolution that FATES has been run at, or like highest resolution that's supported? You mentioned the sunlit and shade levels. Are both of them dynamically growing? Because then you also said the cohort is by size.
So that's, yeah, okay. The first one, FATES, we are running at, you can run it at a point scale, so that's kind of spatially not explicit. But then I don't know what the smallest resolution it's been run at, but I think that really depends on your like driver data. So like you would just need a surface data set that is at that resolution. And really what we're limited by in FATES is time, so it takes longer to run because we're running cohorts instead of like one big leaf per PFT. And then parameterization, so yeah. And then for your other question, so I should have explained. The shade and sunleaf are for big leaf CLM. So when we're running not with fates, we kind of have like 2 canopies of PFTs. And then with fates, we're actually running individual cohorts, and we don't really think of it as a sun versus shade because we're kind of doing all of the cohorts as they're shading each other.
Okay. And then how do you use the TRI database for, because I think, isn't that at species level? So yeah, how do you aggregate that up?
Yeah, well, you'd have to decide what you think. It's kind of irritating. I think I've been working with it and trying to like decide. I mean, if your PFT is something like, deciduous versus evergreen, that's like not very difficult to do by hand. I don't know of any databases I don't think the TRI database has for all of its data. You can actually request to get, there is data on like, is this an angiosperm or gymnosperm? But that may not cover all of the data that you actually want. And so you'd probably have to go in and say like, well, I'm looking for these species and I know these species are, deciduous. Yeah.
Thank you for the nice talk. Can we go back to the land cover sync, the figure?
Land cover? Oh, the land sync?
Yeah. For the future projection.
Oh, future projection. Yeah.
I think we have
forward.
Figure for twice.
Sorry. No. Okay. Sorry.
You can escape and just search.
Okay. All right. Let's see. Okay. Here we go. Yeah, I like moved my slides around, so that's my excuse. Okay, yeah, this?
For the future projection, the vegetation model here we use, is that the dynamic vegetation, or we just use prescribed vegetation climatology?
No, well, it's not, so dynamic vegetation, when you say dynamic vegetation, like I think like a fates type model. So no, we don't have that, but we are using fully coupled biogeochemistry. Yeah.
These are, I guess my questions are active area of research, but I wanted to hear your thoughts on them. For example, I think modern study, we know that plants, they only do CO2 fertilization up until a certain point, and then somehow they plateau out.
Yeah.
But it seems like we think that the uncertainty in the land sink is because of CO2 fertilization. And me and my advisor think the same. But what do you think are the missing link then between modern study, right, and the long-term, I guess, CO2 fertilization effect?
I mean, I think we don't really know how CO2 fertilization works. Like we've done all these face experiments. It's pretty like ambiguous, like if it even happens sometimes, like, and then we know they're going to be limited potentially by nitrogen. And I think, I think we don't really know exactly how the fertilization happens, how kind of acclimation, how if plants are going to acclimate to this, so I think it's kind of at a process level, even plant physiologists don't really understand how fertilization works. And until we really get a handle on that, I think we can't say that that this is like how it's going to happen in 140 years. So yeah, I agree with you and your advisor. Yeah.
Very nice talk. So can you go to the slides where you have a lot of definition of like GPP?
Yeah.
Yeah, so for this slide, so to calculate MBP, so you also need the land use, harvest, and also fire emissions. I'm wondering, for these kind of variables, do you get them from satellite data, or you use the model to
This is the model, yeah. So within the model, we have land use, we have harvest effects, and we have fire. And so this is all within the model. You can certainly compare it to observation based assessments of these values as well, but yeah.
So then the question is, how do you simulate fire, land use, and harvest in the model?
So it depends on what model you're using. In sort of the default CLM, we use the Lee fire model. I'm not exactly sure how it works, but essentially a lot of it is driven off of burned area, or what we know how burned area works. And so we're not, because we don't have dynamic vegetation in fuels, I think we can use what in FATES we have Spitfire, which is based on fuels on the ground, as well as we have canopy fire, and so that all feeds back into each other. And then for land use, we have like an actual land use model that simulates harvest, wood harvest, and crops and changing land cover type.
Thank you so much for your talk. I was wondering if you knew whether and how the model can distinguish between, say, a spot fire, a wildfire, and maybe prescribed burning or other types?
I don't think it can. But like a surface fire, we do have in FATES we can represent surface fire versus canopy fire, and I think we are working on adding that into the main branch where we can have actual active crown fire. In terms of prescribed fire, I don't think we have that. I mean, we don't have that in FATES. I don't think we have that in the Lee model. I don't know. No, Sam is shaking his head. No, we don't. Yeah, if you want to ask about the Lee model, you should ask Sam in the back corner. But yeah, but those are like really important things to add for sure.
All right, other questions? We got a couple more here.
One more thing, we had a really heated discussion last week, I think in Palo Camp, about whether plants facilitate weathering, right? And then that weathering feedback.
Like rock weathering?
Yeah, the silicate weathering feedback.
Okay.
Is significant in the carbon cycle. Do we have plant facilitating like enhanced weathering in our model yet?
I do not know the answer to that question. I don't think so. I really doubt it. But yeah, I mean, that's cool. It's definitely a part of the carbon cycle, for sure. Yeah, I don't know. That could be, just something you could look into. You can ask. Dave would know. He left, but yeah.
You can be on that.
But yeah, you could be here and you could say like,
slide.
I'm adding rock weathering. Yeah, very cool.
All right, hang on, we got a couple more.
You mentioned that GPP, and I wasn't sure if you said autotrophic or heterotrophic respiration, are tightly coupled, which leads to damping
of the interanimal signal. Yeah.
What did you mean? I was confused about that.
So the coupling between GPP and respiration in plants so heterotrophic respiration is very tightly coupled, meaning that like basically we kind of have one key off of the other. And so if you look at this, I'll go back to the Mauna Loa curve. Here's one that's kind of. So the amplitude of if you look at the amplitude of the peaks and the troughs, it's actually, I think it's increasing over time. And that we actually aren't really representing this interannual variability between the peak and the trough of this CO2 signal very well. And we think it's because we have this tight coupling between GPP and respiration.
All right. Yeah, go ahead and pass that across.
Yeah, thank you. I was just wondering if you could say a little bit more about how stomatal conductance is parameterized, and there was one type of stomatal conductance on the side, and you said there was another.
Yeah. So we use right now what's called Medlin. It's similar to Ballberry, but it's just a way of calculating stomatal conductance. So through, depending on moisture availability, like how plants respond to that moisture availability, and then how much transpiration we actually get out of the stomata. And so there's just different equations, and they use different parameters, basically. The intercept, I think, is usually the same. It's the slope that is like the big difference between the two models. And so those are kind of the big PFT specific parameters that you can pick is slope and intercept. And that's part of what's in the PPE, we're looking at that. There's probably other people who are way better experts at Medlin's to model conductance than I am, but yeah.
Can you pass it back behind you too? A little less running for me.
Thanks. I was wondering if you could talk about whether there's feedbacks between the CAM-CHEM model and this model in terms of like emissions of carbon and nitrogen from the landscape that are then processed in the atmosphere and come back down through dust and rain deposition.
Yes. So in a fully coupled model, we do have emissions from the land that affect the atmosphere, and then we do have, I don't know about carbon definition, we do have nitrogen deposition in the model. Yeah, but you would, I've actually never run a fully coupled simulation because you have to do the whole, Earth, and it's very computationally intensive, but yes, like we do have that with all the bells and whistles turned on.
I just want to emphasize, people can think if they have one more question. There are a number of us who work at NCAR who kind of work with one configuration of the model and haven't run other ones. So like I've never run an F case, which is, I think, atmosphere land only. I know it exists, but you can still be very productive even without only using the fully coupled model. So I just wanted to emphasize that it really takes like a huge team of people with different expertise to make this work, which is why when you come up to me and you ask, or you come up to Adriana and you ask something about the sea ice model, she'll be like, I have no idea.
And I have no idea about the sea ice model.
But I think the key is, yeah, I think the key is that NCAR is this community where we know other experts. It's really collaborative. And so if I don't know, I'll go find Adriana and be like, okay, how does this thing work? Help me figure out what I need to know for this, but I am not an expert in that. All right. Any last questions here?
Thank you. So what do you say is the advantage of using the leaf area index in terms of getting an estimate of surface fluxes from different plants as compared with the like NDVI, for instance?
Oh, NDVI. Yeah, we don't simulate NDVI, but NDVI saturates at high LAI levels, so I think that would be a big deal. And LAI, basically it's a proxy for how much plant there is, how much stomata there are, and so that kind of would give us how much flux there is going to be, how much transpiration. So that's kind of what we think of in terms of modeling world of like, if we know how much LAI there is, we can pretty well tell how much transpiration there is going to be if we have those parameters constrained well, and that can tell us what the coupling is between the land and the atmosphere is. Yeah, but NDVI, NDVI is a really great tool for measuring, like observing the Earth. It's kind of actually really hard to observe LAI. It's pretty easy to look at greenness, which is NDVI, but that saturates at high LAI levels, so that kind of confounds things.
Yeah. Okay, well, thank you again, Adriana. It's now a break. We'll come back in here at 10:30. We'll start the morning lab session. We're going to divide up kind of like we did yesterday. I want to emphasize that if you feel like you're behind, you are not. People go at different paces. It's totally fine. So we're gonna try to divide up and make sure people can get the help that they need for whatever they're working on. And if you had a loaner laptop yesterday that you left here, they should be with Elizabeth if you have not already grabbed those. You can talk to her to pick that up. All right, we'll see you back here at 10:30. There's food out there. All right, we're going to go ahead and move into this morning's lab session pretty soon. One thing I wanted to point out, because I think there's been a little confusion, these Meet a Scientist groups, you're meeting in a small group. You're not meeting one-on-one with the scientist, but the idea is to have a small group so that you can all get a chance to talk. So again, with this, share the air, make sure that when you're in your group, everybody gets a chance to ask questions if they want to of whatever scientist you're meeting. But we just think, when you're with your peers, sometimes someone will ask a question that'll spark you to have another question, stuff like that. And so that's why we're not doing it one-on-one. And hopefully if you can start to make connections, then you can continue these conversations either with your peers or the scientists or whoever they might point you to later on. All right, so next on our agenda, and I'm gonna just point this out again because after this we break. So the next activity is the morning lab session. We have a reservation in the queue. I pointed everybody to how to do that this morning. But just in case you forgot, under resources, there's NCAR HPC environment. At the top, we list the queue names and we give the commands for how to use that particular queue. And your lunch is scheduled from 11:30 to 1. The scientists will actually be there to meet with you from 12 to 1. So you might want to get your food and then go to these rooms. And again, if you have questions, I'll hang out down here in the lobby until about noon. And I can point you to those rooms as needed. If you're not doing Meet a Scientist, you can go on a walk, whatever. And then at 1, we're gonna meet in this front lobby. And if it's not too hot, we'll go outside for a nice picture. If it's really hot or too bright or whatever, then we'll stay inside in that front lobby. So just reminding you to be back here at 1 to be in that picture. And yeah, so without further ado, the next speaker is Hui. She studies climate variability and change, primarily tropical, I believe. And she's also part of the CESM tutorial committee, so she is essential for having put on all of this.
First time using this. Can you hear me all right? Yes. Hi, everyone. I'm Hui. I am a research scientist here at NCAR. So I'm just going to give you a brief overview of today's lab session where we will learn about simple XML modifications. So the XML files, you may have already seen it in yesterday's lab, and some of you may already have experienced of modifying them. So today's goal is to kind of give you a more systematic understanding of the XML files and how we usually use them for. So this is the outline for today's lab. We'll first learn about the basics, what are XML files and how to modify them. And then we're gonna go into the meat to learn about how to control the length of your run. This includes how to start and stop, restart, and how to specify your run for a long simulation and how to use timing files. And then we're also gonna learn how to modify the type of run, and also the material will cover how to modify the physics time step for certain model components. And we'll end with 3 exercises, 3 little exercises that will help you better understand how things work. So I'm just gonna go over it briefly, the basics. So what are the model control files, or these files with the file extension XML? So yesterday we learned that the basic workflow of running your CESM consists 4 basic steps, right? You first create your new case, and then you set up your case, you build it, and you submit it. And after you create your new case, if you take a look at your case directory, you'll find a bunch of new files appearing. And several of them has this file extension called XML. And these are the user customizable case XML files. We also call them model control files. So we use these files to control how we want to compile and run our model. These files, again, appears when you invoke the create new case command. And there are a bunch of them. In the material online, you will find a brief description of each of the files, what they do. And I also encourage you to just open up the files to go over the variables to learn what you can control with these. And they will become in handy when you actually run your CESM case for more advanced applications. But in today's lab, we're going to focus more on the env-run.xml. So this particular file controls how you run your model. We can specify the length of your run, type of your run, etc. And that will be the main lab session. The main lab session will be about this file. So now we know what XML files are. How do we go ahead and modify them? There are actually 2 ways, but we highly recommend that you use the XML change command. This is a tool you can find in your case directory. And then alternatively, you can also just use your favorite text editor to open up the file and change the values directly. But in doing this, you have to be careful of not introducing any errors in formatting or syntax. And the reason we recommend using XML change is not because it's very simple, and also because it can automatically get recorded in your case status file. So when you go back to your case status file, you can take a look at the history of what you have done with your XML file modifications. It's always good practice to keep track of what you have done. You may think you remember everything in 3 months, you'll remember nothing. Speaking of experience. Yes, then how will we use it? It's kind of very straightforward, actually. I give you an example in here. There is a variable called continue run in the mrun XML file. Now, the default value of this variable is false. How do we change it to true? And this is the syntax how we want to use it, which is ./XML change followed by space, and then the variable name, here's the continue run, and equals the desired value of your new value. So this is the continue run equals true. So quite straightforward to use. So that was modifying. Then how do we search for a variable value? So for this, we can use another tool. Again, in your case directory, it's called XML query. For this, here is an example. It's even easier. You can just run ./XML query followed by the variable name. Here we're looking for this variable called run type. So if you type this, it will return the value of the run type. Here for the default case, it should be hybrid. So for both of these tools, XML change and XML query, you can always use execute command --help, and they will list a whole bunch of information you will ever need for these two tools. So always use this help if you forgot anything. So that was the basic introduction of the XML files, what they are, how to control, how to modify them. And then the main part of the lab session today is to learn how to control the length of your run. So the length of your model run is controlled by several runtime variables, and these are all in the mrun.xml file. And these variables can be modified at the time when you initialize the run or during the course of your run. And in the tutorial lab session today, we will learn about how to customize your runtime settings to control how to start, stop, restart, and continue a model run, and practice how to specify the run length of your long simulations. So I will just go over briefly several variables that are related to your runtime. Hopefully this will give you, a brief start. So the first two variables you want to know are called stop option and stop run. So the stop option, these two variables are all in the mrun.xml again. So the stop option says the run length time interval type. It could be, for example, n months, n days, or n years. And the stop n variable says the number of intervals set by the stop option to run the model. So for example, if we want to run a simulation of 6 months during this one job submission, we can set these two variables as stop n equals 6 and stop option equals n months, right? It's kind of straightforward. And just notice that stop n and stop option, these two variables control the run length of your run per job submission. And your typical simulation is comprised of many job submissions. Imagine you want to run 100 years, but you couldn't really do it in one go. This is because you can only stay in the computer queue for a limited time. So we'll have to specify multiple submissions in order to complete your long simulations. And we will learn about that again, in today's lab session. But before that, there is a very important concept we need to understand. When you submit a job, batch job submission, your run can either be an initial run or a continue run in terms of your long production model run. So initial run is when your run is first initialized, like the exercise you did yesterday, right? It starts from nowhere, from the very beginning, I mean. So there's a variable called continue run in the mrun.xml. So this variable is kind of a flag telling the model if your current run is starting from the very beginning or it continues from a previously completed batch submission. So if you set the continue run variable to be false, and then the model recognizes it, and then will try to run your model simulation from the very beginning. And now if you set it to true, the model knows, okay, this is a continue run, so I want to search for the restart files and continue your previous simulation as if it has never been stopped. So this is a very important concept when you run your model simulations. So for example, here we say we submitted our initial job. with the continue run equals false, because this is an initial run. Now, if your run has been finished and you check everything looks good, and now you want to continue this run for another month, what do we do now? You have to tell the model, now we want to continue from the previous run, right? So you need to go into the env_run.xml and use XML change to change this continue run variable to be true. And now you submit the run again, so the model can carry on with the simulation. So at the end, the model will continue run with a bit-for-bit match as if it has never been stopped. And at the end, you will have 2 months of simulation. So for example, if at this step you didn't go ahead and change the continue run to be true, it still stays to be false, and you submit your run again, what would happen? The model will run again from the very beginning for a month. So at the end, you still get 1 month, the first month, right? Understand? So now we covered that these two variables, stop in and stop option, controls the run length for each job submission. And we have to submit multiple jobs to finish your long simulations. So now we have to specify the number of submissions, right? So this variable called resubmit, it specifies the number of times you want to resubmit your job. This variable is again in the env_run.xml. So the total number of submission of your run equals your initial run plus the value of the resubmit. For example, if you set resubmit to be 2, to be 1, and then you submit your initial run, the model will run for the first job submission, and the end, it recognizes resubmit is 1, and then it will run again. So in total, you get 2 submissions. Okay, and remember we talked about continue run, and there is an interesting relationship between these two variables. Now, if you set your resubmit number to be a value bigger than 0, the scripts of your model will automatically change the continue run to be true after the completion of your first submission for all subsequent submissions into the queue. So this is a note you have to remember. You'll get to know more about this in your tutorial material, so it's okay if you don't get it now. Okay, now we've covered how to run long simulations. I'm gonna give you a little quiz. Let's say the tutorial version of the CESM model, on Cheyenne can simulate 10 model years per walk clock day. That means for 24 hours walk clock, you can run 10 model years, right? Now, the maximum walk clock request for your job submission is 12 hours. And now, let's say we want to run this model for 100 years. What values should be set for stop option, stop in, and resubmit? Now you have 5 seconds to think about it. And I'll randomly ask one of you to answer it, okay? Just kidding. Let's just go over this together, all right? So we know that the maximum walk clock request is 12 hours. Let's say we want to use the full 12 hours for our job submission. And we already know that the model runs for 10 years per walk clock day, that means 24 hours. So for our job submission of 12 hours, we can only run half of it. So we can run 5 years per job submission, okay? And then one option we can have is that we can set stop option as n years and stop n as 5. So 5 years per job submission. But how many times in total? 20 times. If it's 20 times submission, we need to set the resubmit number to be 19 because the initial run of 5 years plus 19 resubmission of 5 years is 100 years, right? Nice, I think most of you get it. But this example is also included in the material we'll go over, so no worries if you don't get it now. So that was the runtime, the kind of the content of how do you control your runtime and run length. And then in the lab, we'll also cover how to modify the type of run. This kind of, the type is you need to specify it for your initial run. There are 3 types of the CESM run. It could be a startup, a branch, or a hybrid. I won't go over the details, but no, this is kind of an important concept when you want to start a production run. You have to go over this by yourself. One important note is that the XML variable run type determines the initialization type and means that the run type setting is only important for the initial run of your production run when your continue run variable is set to false. Okay, and after initial run and when your continue run variable is set to true, the model will restart exactly as the input file, by a bit for bit continuous fashion. And at this time, your run type setting is no longer relevant. All right. And I also put a note here, but it's too complicated. I won't go into it. This basically says if you want to run a hybrid or a branch, you'll have to do an extra step of setting some reference variables and also put restars file into your run directory. Anyways, you will find all this information in the material, so don't worry. Yes, so at the end, we will have 3 exercises where we will practice runtime variable modifications, and you will try to create a branch run and modify the ocean coupling frequency, and at the end, you will try to create a hybrid run and modify the atmosphere physics time step. And that's all I have. I hope you have fun in the lab session.
All right, thank you. And I just want to emphasize some of this might seem a bit over the top, and even things like the hybrid versus branch, I get confused about sometimes, and I go back to the ENV run, and I'm like, what is each one? How are they different again? So it's not at all abnormal if you're thinking like, I don't quite understand how those things are different, or to go back and look, because I almost all my documentation is for myself in the future when I'm like, what on earth did I do? So I think that's pretty important. So we're gonna break out into the different groups now to start this first lab. I wanna kind of break out, we wanna be able to get people the sorts of expertise they need. So if you are working on the basics from yesterday, can you raise your hand? There's no shame in this. If you did not complete exercise 2 of basics, nobody's gonna raise their hand because they're embarrassed. There's this part where it was extending your run to run for a whole month. So everybody in this room completed that successfully. All right, okay, cool. All right, so I guess we don't need to worry too much. We'll just break up again by groups. So the simple XML, a lot of what you're gonna do today is just start reading through some of this. You might start the exercises, but our intent is that you'll read over a lot of this material before you start the exercises, because that has the information you need to successfully complete the exercises, which are kind of like a test of if you understood it. So if you have already completed the XML modifications, I'm not going to ask people to raise their hands. If you could just come talk to me at the front at the end, we'll figure out where those people are and see, because people came in with different levels of having run this before. So we'll kind of just do the split again. This side of the room goes to the library. This side of the room can go to the Damon room, unless you're one of those people I suggested come talk to me.